This is Ramakrishna. In this video class, we are going to discuss about composite functions and its properties also. Now, what is the definition of the composite function? Here I am taking three sets A, B, C, and the three are non-empty sets. Here f is the function mapping from A to B, and g is the function mapping from B to C, B2 functions. Then g circle f mapping from A to C is called the composite of f and g, and that is defined by g circle f of x equals to g of f of x. A, B, C. F is the mapping from A to B. Here x be an element in a set A, y be an element in set B, z be an element in set C. F is mapping from A to B. So f of x equals to y. And g is the mapping from B to C. So g of y is equals to z. G of y is equals to z. Here then what they are saying, that g circle f is mapping from A to C. The g circle f is mapping from A to C. Now here you can see the domain of, here g circle f is mapping from A to C, they are saying the domain of g circle f is the domain of f only. Now if I take g circle f of x, that is equals to g of f of x, that is equals to g of f of x equals to y, and what about g of y, that is equals to z. So here we got g circle f of x equals to z. Here f of x equals to y means f is mapping from A to B. G of y is equals to z means g is mapping from B to C. G circle f of x equals to z means g circle f is mapping from A to C. Next, here first theorem we can discuss. F is mapping from A to B and g is mapping from B to C are 1 1. Here f is 1 1, g also 1 1. Then g circle f is mapping from A to C is also 1 1 there. Here how to prove that one? Here what is the analytical method? By using the analytical method also previously we proved the given function is 1 1. What is that one? For example, x1 comma x2 belongs to the domain of f. A, x1 comma x2 belongs to A. Here f of x1 is equals to f of x2. That implies x1 is equals to x2. Then we say f is 1 1. If f is 1 1, f of x1 is equals to f of x2. That implies x1 equals to x2, where x1 comma x2 be any two elements in the domain of f. Now here also I am taking what is the domain of g circle f, that is the domain of f only, A. Here also I am taking any two elements, let x1 comma x2 belongs to A and g circle f of x1, that is equals to g circle f of x2. Here how they define the composite function g circle f of x, g of f of x1, that is equals to g of, that is f of x2. Now these are the two elements in the domain of G. Those are the two elements in the domain of G. So g of x1 is equals to g of x2, and g is 1 1 function already given. G is 1 1 function. So g of x1 is equals to g of x2. We can write x1 is equals to x2. Here in the place of x1, f of x1 is there. In the place of x2, f of x2 is there. Since g is 1 1. That's why g of x1 is equals to g of x2. That implies we can write x1 is equals to x2. Now that implies f of x1 is equals to f of x2. Here we can write x1 is equals to x2 since f is 1 1. Why? Because f is 1 1. F of x1 equals to f of x2. That implies we can write x1 is equals to x2 only. Now here what we got, g circle f of x1 is equals to g circle f of x2. That implies we got x1 is equals to x2. Therefore, g circle f is 1 1. G circle F is 1 1. Here both F and G are 1 1, then G circle F also 1 1 function. The diagrammatic also here I am showing. Here I have taken two elements x1 comma x2. You can take any two elements in the set A. Here F is mapping from A to B. What is the image of x1 under F? That is F of x1. The image of x2 under F, that is F of x2. And G is the mapping from B to C. The image of F of x1 under G, that one we can write G of F of x1. And the image of F of x2 under G, we can write G of F of x2. Here G of F of x1, here this is the G circle F is mapping from A to C. So here I am taking x1 comma x2 belongs to A. Here G of F of x1 is equal to G of F of x2, that implies x1 is equal to x2. Then we say G circle F is 1 1. Next theorem, F is mapping from A to B and G is mapping from B to C are on two functions. Then G circle F mapping from A to C is also onto. Here, what is the onto definition? Here a definition very important. For example, here, if F is onto, for every y belongs to B, there exists an element x belongs to A such that F of x equals to y. For every y belongs to B, for every element in the codomain, there exists a pre-image. There exists an element x belongs to A such that F of x equals to y means there exists for every element in the codomain, there exists pre-image only. Then only that is said to be onto. Every element in the codomain should be mapped with at least one element in the domain. Now here we can see A, B, C. Here what they given? G is onto. Given that G is onto. Therefore, for every Z belongs to C, there exists an element Y belongs to B. There exists an element Y belongs to B such that G of Y is equal to Z. This is first point. Here G small g you can write. And one more thing also given, F also onto. Also given that F is onto. F is onto means here F is onto. F is mapping from A to B. For every y belongs to B. For every y belongs to B, there exists an element x belongs to A such that F of x equals to such that F of x equals to y. Keep aside these two. Now here F is mapping from A to B and G is mapping from B to C. Then G circle F is mapping from A to C. If G circle F is onto, we have to prove that for every Z belongs to C, there exists an element x belongs to A such that G circle F of x equals to Z we have to prove. G circle F of x equals to Z. If G circle F is onto, here G circle F of F is mapping from A to C. If G circle F is onto, we have to prove that for every Z belongs to C, there exists an element x belongs to A such that G circle F of x equals to. We have to prove that G circle F of x equals to Z. Now I have taken this one. What is the how they define the composite function? G of F of x. That is equals to G of. Here we got F of x equals to y. And G of y is equals to Z. Therefore, G circle F of x equals to Z we got. Therefore, for every Z belongs to C, there exists an element x belongs to A such that G circle f of x equals to Z. Therefore, G circle f is onto. Here next, if f is mapping from A to B, G is mapping from B to C, and G circle f is 1 1, then f is necessarily 1 1. Compulsory it should satisfy 1 1, but G may not be 1 1, may or may not be 1. Now here you can see the diagram. F is mapping from A to B and G is mapping from B to C. Here I am taking 1, 2, 3, 4. Here 1, 2, 3, 4, 5, 6 I am taking. Here also 1, 2, 3, 4, 5, 6 I am taking. 1 is associated to 1. The image of 2 under F is 2. The image of 3 under F3 I am taking. Now by observing this one, F is mapping from A to B. Here different elements having the different images. So F is 1 1. F is necessarily 1 1. Now here 1 2 1. The image of 2 under G, that is 2. The image of 3 under G I am taking 3. Next the image of 4 I am taking. The image of 5, the image of 6 also 6 I am taking. Now here you can observe F is 1 1, but here what about G? At least 2 elements having that. This is not 1 1 only. This one we say many to 1. F is 1 1, G may not be 1 1. Here G is not 1 1. Now here we can write G circle F. What is the domain of G circle F? That is the domain of F only. G circle F is mapping from A to C. F is also mapping from A to B. So both are having the same domain. Here last whatever be the function is there, its domain is equal to the domain of last function only. The domain of G circle F is the same as the domain of F. Now if I take 1, otherwise here we can write G circle F of 1, that is equal to G of F of 1. That is equal to G of, what is the image of 1 under F? That is 1. G of 1 is equal to 1. Like that we can complete all. I am writing all these. If I take 1, we are getting the image of 1. By taking 2 only. By taking 3. By taking 4. Now here you can see 4 we are getting. G circle F. That is mapping from A to C. Here also by different elements having the different images. So here we say G circle F is 1 1. G circle F is 1 1. Here F necessarily compulsory, that is 1 1. But G may be or may not be 1 1. Then also G circle F is 1 1. Now F is mapping from A to B, G is mapping from B to C, and G circle F is onto. G is necessarily onto, but F may or may not be onto. This one also with example we can discuss this one. F is mapping from A to B and G is mapping from B to C. Here I am taking 1, 2, 3, 4. Here 1, 2, 3, 4, 5. Here 1, 2, 3 only I am taking. Now F is not onto. Here F is not onto. Why? Because at least one element in the codomain doesn't have pre-image. Here 5 doesn't have pre-image. So the F is not onto. All the elements having the pre-images, then only that function is said to be onto. F is not onto. Now what about G? That is onto. G is mapping from B to C. All the elements in the codomain having pre-images. So G is onto. F is not onto here. Now here we can write G circle F. What is the domain of this one? 1. g of f of 1. That is equal to g of, what is the image of 1 under f? That is 1. G of 1 is equal to 1. Like that, for the remaining also I am writing here. G circle f. By taking 1, 1. By taking 2, 2, 2, 2. By taking 3, 3. By taking 4, 3. Here G circle F is mapping from A to C. Here C is the codomain. In the codomain, what are the elements are there? 1, 2, 3. And what is the range of G circle F? That is also 1, 2, 3. So the range of G circle F is equal to codomain. So here we say G circle F is onto. G circle F is onto and F is may not be onto, G necessarily onto. Next, one more. F is mapping from X to Y, G is the mapping from Y to Z, and H is mapping from Z to Z. Here the composite of three functions are given. Here we have to prove that H circle G circle H of X equals to H circle G circle F of X. This one we say associative property. Now I am taking H circle G circle H of X. H circle G circle H of X I am taking. Now that is equal to, now this is in the form of, see here previous G circle F of X equals to, how we define that one? G of F of X. So this one you can consider G, this is F1. G circle F of X. So G of H of F of X. This is F of X. G circle H of X. ಒಂದು ನಿಮಿಷ here we have to prove that H circle G circle F of X equals to H circle G circle F of X. So left hand side, this one I am taking H circle G circle F of X, that is equals to the, here composite function of G and F. How we define that one? G circle F of X equals to G of F of X only. So this one you can consider G, this one you can consider F only. G circle F of X, that is equal to G of means H of G of F of X. F of X means G circle F of X. And again that is equal to H of, this is in the form of G circle F of X. We define that one G of F of X. So H circle G circle F of X equals to H of G of F of X, you can write. And one more, H circle G circle F of X, that is equal to, this one also, this one you can consider G only. G circle F of X equals to G of, in the place of G, H circle G is there, G of F of X. This is also in the form of G circle F of X, G of F of X. Now that is in the form of G circle F of X. This total you can consider X only. G circle F of X you can write G of H of G of F of X. Now here you can observe these two. Right hand side we got the same thing only. So these two are equal. Now we can discuss some problems related to composite function. Here f of x equals to x square plus x plus 1 and g of x equals to sin x. In general, f circle g is not equal to g circle f only. F circle g is not equal to g circle f. Sometimes it depends upon the functions. Sometimes we can get equal, but we can't say. But based on that, we can't decide that one. Both are equal. In general, most of the times we can't get that one. So that is not a commutative property. F circle g is not equal to g circle f. Now here we have to find f circle g and g circle f. F circle g of x. How to define that one? F of g of x. That is equal to f of, what about g of x here? That is sin x. Now here f function is there, f of. While writing the f function, in the place of x you can replace this function, this term. So here f function is there. While writing the f function, In the place of x you can replace sin x. Here x is there. In the place of x you can replace this sin x only. Sin x whole square plus, again x is there. In the place of x you can put sin x plus 1. This is f circle g of x. Next to g circle f of x. That is equal to g of f of x. Now g of, what about f of x here? X square plus x plus 1. Now here what I am saying, g function, you can write down the g function in the place of x. Here x is there. In the place of x you can replace this one, x square plus x plus 1. While writing the g function, wherever you get x, in the place of x you can replace that value only. Here also we have done the same thing. While writing the f function in the place of x, I substituted this sin x only. Sin x whole square plus sin x plus 1. Now this one, g circle f of x equals to this one. Here both are unequal. Next. Now f of x equals to x plus 2 by x plus 1. G of x equals to x minus 2 by x. Here find the domain of g circle f of x, f circle g of x, f circle f of x and the g circle g of x. So first one I am going to explain here. F of x equals to, g circle f of x equals to, this one we can write g of f of x. G of, what is f of x here? X plus 2 by x plus 1. So here this one doesn't exist for x equals to, x should not be equals to minus 1. Now while writing g function, in the place of x you can replace this one only. Here x is there. In the place of x you can write this one, x plus 2 by x plus 1 minus 2 by, in the place of x you can replace this one, x plus 2 by x plus 1. Now here you can simplify, x plus 2 minus 2 into x plus 1. Here I am taking LCM only, by x plus 2. Here both the denominators gets cancelled. Now here x minus 2x minus x plus 2 minus 1 plus 1 by x plus 2. So this one g circle f of x, this one doesn't exist for minus 2, x is not equal to minus 2. Overall, what is the domain of g circle f? Domain of g circle f, that is equal to, here wherever we are writing this, here we f of x I substituted that one. This one doesn't exist for x equals to minus 1 and this one doesn't exist for minus 2. So for the remaining all the real values of the g circle f is existing only. Or minus, we have to subtract minus 1 and minus 2. Except these two values, the g circle f is exist for every real value. In one quarter. Second one, f circle g of x, that is equal to f of g of x, f of, what about g of x here? X minus 2 by x. So this one doesn't exist for 0, x should not be equal to 0. Now here f function is there. While writing the function f, in the place of x you can replace this one. Here x is there. In the place of x you can write x minus 2 by x plus 2 by, here x is there. In the place of x you can replace that one, x minus 2 by x plus 1. Now here you can simplify this one, x minus 2 plus 2x upon x minus 2 plus x. Here both the denominators gets cancelled. Here this is a 3x minus 2 upon 2x minus 2. And here this function doesn't exist for 2x minus 2 is not equal to 0, x should not be equal to 1. This is f circle g of x. Now what is the domain of? Domain of f circle g of x is equal to, exists for every real value except 0 and 1. This is the domain of f circle g. And rest of the problems you can practice, and I will give one more problem also for practice. Here this one for practice, otherwise here also I will explain one bit, remaining all you can practice. Here I am finding the domain of f circle g of x, finding the function f circle g of x, composite function f circle g of x, at the same time finding the domain of f circle g of x also. F circle g of x, that is equals to f of g of x, that is equals to f of, what about g of x here? Square root of 2 minus x, square root of 2 minus x. So here x doesn't belongs to, here 2 minus x should be more than 0 only, 2 minus x should be more than or equals to 0, x is less than or equals to 2. So here x doesn't belongs to, for all these the function exists only, so x doesn't belongs to 2 to infinite. Minus infinite to the function exists only, for 2 to infinite the function doesn't exist. So here I have written that one. That is equals to, what is f of x here? Root x is given. Root of, in the place of x you can replace this one. Square root of 2 minus x is given. Here also the same thing only. So here we can write r minus, here we can write r minus, this one exists for every real value except 2 to infinite. Or this is the domain of f circle g, r minus infinite to 2. This is, both are same only. This is the domain of f circle g of x. Next, here we can solve one more. F is mapping from R to R, be the function defined by f of x equals to, here f of x equals to, what they given? A into x square minus root 2 is given. For some positive a, here f circle f of root 2 is equals to minus root 2, then we have to find the a value. And whatever the a value, a should be positive. If we get negative and positive, here we have to consider only positive value. And here what they given, f circle f of root 2, that one we can write f of root 2. That is equals to a x square minus root 2. Now, what is f of x function? Wait a minute. Here f of root 2, that is equals to, here minus root 2 is given. F of, what is f of root 2? In the place of x you can put a root 2, a into root 2 whole square, that is a 2 minus root 2, that is equals to minus root 2 we got. Here, next, again this is in the form of f of x, f of x equals to a into x square minus root 2, a into, in the place of x you can replace that one, 2a minus root 2 whole square minus root 2. Here f, this is in the form of f of x, in the place of, while writing the function f of x, in the place of x you can replace this one, a into 2a minus root 2 whole square minus root 2, that is equals to minus root 2 is there. Now here minus root 2 we can cancel, and here we got a into 2a minus root 2 whole square, that is equal to 0. Here two possibilities are there, either a is equal to 0 or this one should be equal to 0. This is the perfect square, that is equal to 0, possible only when 2a is equal to 2a minus root 2, that is equal to 0. Here a is equal to 0, and one more we got, a is equal to root 2 by 2, that is 1 by root 2 only. Here two values we got, but here what they mentioned, some positive a. In this, what is the positive value of a? A is equal to 1 by root 2. This is the answer. Okay, thank you.